Look down at Earth at night, continents outlined by city lights, oceans black and endless. Above that glow, thousands of satellites race silently through the dark. Their signals are invisible, but their impact is everywhere, linking people, guiding ships, watching storms, and syncing the world's clocks with astonishing precision. In a single day, you tap directions, stream live TV, check a radar map, and message someone across an ocean. It feels instant, like magic. But the answer is orbiting thousands of kilometers overhead. Have you ever wondered how your phone knows where you are? Satellites make it possible. So, what is a satellite? In the simplest sense, it's anything that orbits a larger body. The moon is Earth's natural satellite, held by gravity and moving fast enough to keep circling instead of falling straight down. Humans copy that idea, building machines that orbit with purpose. Artificial satellites begin on the ground, packed into a rocket like a fragile instrument inside armor. When the rocket climbs beyond most of the atmosphere, it releases the satellite into the vacuum of space, where there's no air to fly through, only orbit to fall into, and sunlight to harvest. Once deployed, a satellite unfolds like a mechanical flower. Solar panels swing out to drink sunlight, antennas extend to talk with Earth. Inside, batteries store power, computers run commands, and sensors do the job, taking images, measuring signals, or relaying data. Everything must survive alone, for years. To reach orbit, a rocket must do two things: climb high enough to clear the thick air, and accelerate sideways fast enough to keep missing the ground. That second part, speed, demands enormous energy. A modern launch is a carefully timed sequence of engines, guidance, and stage separation. As fuel empties, dead weight is discarded. Stages separate with explosive bolts and precise pushes so the next engine can ignite cleanly. Each separation is a choreography in microseconds, because one wrong angle can spin the payload or waste the speed needed to reach orbit. Higher up, the payload fairing, those protective shells, splits open and peels away. It's like removing a helmet once you're in space. Now the satellite is exposed to sunlight and vacuum, riding the upper stage as it coasts, then burns again to target a precise orbital path. Finally, deployment, springs or a gentle push release the satellite. It drifts free, then fires tiny thrusters to stabilize its spin and point its antennas. Below, Earth sweeps by. Cloud bands, coastlines, and the thin blue atmospheric edge that makes our world look so delicate. Orbit feels like floating, but it's really falling. Earth's gravity constantly pulls the satellite downward. The only reason it doesn't crash is because it's moving sideways so fast that as it falls, the planet curves away beneath it. The satellite keeps missing the ground again and again. If the sideways speed is too low, the orbit shrinks and the satellite re-enters. Too high and it can escape. Most satellites live in carefully chosen bands. In low Earth orbit, they whip around the planet in about 90 minutes. Higher up, the paths widen and the pace slows. These orbital regions serve different missions. LEO is great for sharp imagery and low-latency communications, but satellites there need constellations to cover the whole globe. MEO is ideal for navigation systems, and far above in geostationary orbit, a satellite matches Earth's rotation and appears fixed in the sky. Communication is the satellite's real superpower. Ground stations send radio waves upward, packets of information riding electromagnetic energy. The satellite receives that signal, filters it, amplifies it, sometimes shifts its frequency, and then retransmits it back down. Space becomes a mirror for data. From orbit, one satellite can link distant points that can't see each other over Earth's curve. A message can leap from one continent to another in fractions of a second. Modern systems may even pass data satellite to satellite using laser links, forming an invisible mesh above the planet. GPS is different. The satellites aren't sending you a map. They're sending time, ultra-precise timestamps from atomic clocks. Your phone listens to several satellites at once, measures tiny differences in arrival time, and calculates its distance to each one. With 4 or more, it triangulates your position in 3D. Weather satellites watch Earth as a living system. Some stare constantly from high orbit, tracking hurricanes as they spin. Others sweep low over the poles, scanning the entire globe in strips, measuring clouds, water vapor, sea surface temperatures, and even the heat signatures of wildfires. And for broadcasting, satellites act like giant repeaters in the sky. A TV feed goes up from a broadcast center, is relayed by a geostationary satellite, then rains down across a whole region to dishes on rooftops. One spacecraft can illuminate millions of homes at once. Not all satellites do the same job. Communication satellites prioritize bandwidth and coverage. Navigation satellites prioritize timing accuracy. Weather and Earth observation satellites prioritize sensors and stable pointing. In orbit, design is destiny. Every antenna, lens, and circuit is tailored to the mission it was built to serve. Communication satellites can be massive, like the ones parked in geostationary orbit with multi-panel arrays and powerful transponders. Others are swarm, constellations in low orbit that hand connections off from one satellite to the next, keeping internet links alive as they race overhead. Earth observation satellites are our eyes on the planet. Some capture sharp, visible light images of cities and forests. Others use radar that sees through clouds and at night, revealing floods, shifting ice, and ground deformation after earthquakes. From orbit, change becomes measurable, not just visible. Some satellites serve national security, tracking ships, listening for signals, or providing secure communication. Others push pure science, space telescopes that escape Earth's blur and stare into the deep universe, or instruments that measure Earth's gravity and atmosphere. Orbit is a laboratory with no walls.